Hello, it is I, Dr. Brian Lorgon111, and I am back because yesterday I showed off a game of life implementation and asked people to figure out how I implemented it. And today I actually want to show off how I implemented it because it was a puzzle that already two people, somewhat immediately after the video aired, had managed to solve, or at least had figured out kind of the key aspect of. And so I wanted to talk through it. But just as a quick review, you'll recall that in Conway's Game of Life, if there are blocks that only have 0 or 1 live neighbors nearby, they will die of loneliness when I actually run the simulation. If we get up to 3 blocks here, this guy in the middle has 2 neighbors nearby, so he'll manage to stay alive. The guys on the end are going to die of loneliness because they each only have 1 neighbor nearby. However, one of the other rules says that when there is a blank space that has exactly 3 neighbors, such as the space right here and the space right here, a new guy will be born. And so when you have 3 in a row like this, it ends up kind of in this alternating pattern where guys are born on this end and die on this end, and then vice versa. And finally, if we go ahead and kill that off, it is the case that live cells will die of overcrowding. And so if I do something like this, the guy in the middle is going to die because he has 4 neighbors, and so he's going to die of overcrowding, but there's going to be a bit of activity that goes on in all of the other cells nearby. And so that's the game of life. And what's interesting about it is with just those simple rules, you can get some very complex behavior, such as things like these gliders that just go off into the distance forever. And so the question is, how did I implement it efficiently using only one entity? You can see on the screen right up here, it says E equals 1. There's 1 armor stand in the world. And the answer that people managed to guess, and I wasn't sure if this was going to be easy to guess or not, if I actually get this running and I go into spectator mode so that I can fly down below, the answer is command blocks. Which is kind of funny for me because back when 1.9 came out and the new command blocks came out, they basically made Redstone obsolete for programming general computation stuff. And so I said, you know, Redstone is dead, long live command blocks. And when functions came out more recently here in 1.12, I was thinking functions are dead, or sorry, command blocks are dead, long live functions. But it turns out there's still some utility to functions. And I mean, obviously, there's still some utility to Redstone as well. But basically, yeah, in order to keep track of where all the live cells are, I'm actually placing command blocks in the world. And so I thought it could be useful to just go and actually run through all of the code because there's not very much code in this game of life. So let's talk through it. So the way that I have chosen to implement this, there are just 7 functions. I'll probably just start showing text snippets on the screen while I'm talking. If you have better presentation ideas, let me know. There's just 7 functions, and each of the functions is really short, and so we can actually talk through kind of almost every line of code and make it pretty understandable. And so the first one of these functions that I want to look at is the initialize function, and this is just something that you have to run first that's going to set everything up at the beginning. So it's going to create scoreboard objectives, it's going to summon the 1 armor stand into the world and initialize a few values. There are 3 scoreboard objectives that I am using. One is called A, which is going to have a value of either 0 or 1, and is going to iterate between 2 different algorithms we'll run on alternating ticks of Minecraft, and we'll come back to the details of that in a bit. N is a scoreboard objective that's just using for counting the number of neighbors. And so, for example, when you're looking at a particular black cell and you're trying to decide how many neighbors it has, it's just going to count up 0, 1, 2, 3, 4, 5, 6, 7, 8 to figure out how many live neighbors it has. And so that's what N is used for. And finally, R is used for running, which is going to be either 0 or 1. It's going to be 1 if I am holding the block of redstone and the simulation is running, and it's going to be 0 if I am not holding the block of redstone and we're currently kind of paused in the simulation. And yeah, and then I set up some initial values on a couple of things that the details of we don't need to look at right now. Next up is the main game loop function. It's a function called life, and it looks a little bit complicated, but it's actually not doing very much. Basically what it does is it tests and sees if I'm holding the redstone block to set the appropriate value of R. And if we are running, if I'm holding the redstone block, it will also advance the value of A between 0 and 1 so that we can go kind of back and forth between game loops. And then apart from that, it just recognizes the bat and skeleton eggs and does what it needs to do with them, basically setting black wool blocks or white wool blocks if I place down the bat spawn egg or the skeleton egg. And also, and here's the key, setting some command blocks underneath the bat egg. And so if we switch from looking at the code to looking at the screen again, I can show off exactly that. And so basically, if I go into spectator mode, I can see that where I'm at right now, like over there where I'm looking, there's some command blocks, but there aren't any command blocks right below me here. And so if I place a bat spawn egg there to make this a live cell, and we fly back down, now we can see that there's a 3x3 group of command blocks around that live cell that I placed. And that's going to be the general invariant that we have throughout things, which is anywhere there's a live cell, there could be activity at that cell, and there could be activity in the neighbors of those cells. So we actually need to be ready to do some processing work whenever there is a live cell nearby. And so setting up the bat just kind of like sets up that initial condition where we create these command blocks that actually are ready to process cells right above them to decide if there's changes that need to happen in the life simulation. And while we're here inside Minecraft, I can actually right-click on the command block, and you can see what the command block does, and this is the reason functions are so important, is it calls a function. Before functions were introduced in Minecraft in the most recent versions, a command block could only run a single command. Now a command block can call an entire function, which can do an entire set of logic. And so one command block, whose job it is to decide one piece of wool above him, what color he should be next. One command block can do all of that logic with a single command by calling a function that then runs a bunch of other commands that do all of the logic. And so that's kind of the key insight into what's going on. But now let's walk through the rest of the code, starting with check 1, starting with the code that's being called by those command blocks. So next up, let's look at the check1 function, which is the function that the command blocks actually execute. And all of the command blocks that are in the world, all the repeating command blocks that I have, call this function check1. And what that command block does is first it teleports the armor stand to its location. And it's going to be important to have an armor stand at the location of the command block because we're eventually going to be running some commands relative to the armor stand. Things like execute detect, things that allow you to check and see if there is a piece of black wool or white wool in a certain location relative to you, require an entity that they can run relative to. And so we use the one armor stand in the world, and each different command block that's going to run teleports the armor stand to itself and then runs some things relative to it. So that's the first thing we do. We teleport the armor stand. And then, depending upon which iteration of the loop, kind of like even or odd, if we're a equals 0 or a equals 1, we're either going to run something called check1 body or something called check1 part 2, which are not very descriptive names. And the reason that it's staged into these two things that run every other tick is, in general, a common way to implement something like the game of life or a number of other cellular automata type of processes is to use something that is sometimes in graphics called double buffering, where basically the idea is you have one set of blocks that is visible on the screen right now, but you also have another set of blocks which is going to be computing what is going to appear on the screen next. And so basically the way that this is implemented in this life version of Minecraft is at y equals 4, which is the thing that I'm looking at right here, and breaking some blocks. That is the current screen that we are looking at. But where we are computing, there is another layer of wool blocks at y equals 3, one level below it. And that is where we do the computations for what we want to appear in the next tick. And so anything that we're going to display in the next tick, we will first compute it and actually draw it at level 3, and then we'll kind of clone it up to level 4 during the next tick. And we do that so that each individual command block can run each individual XZ cell during one iteration, by reading all of the things on level 4 around it, and then writing just its individual cell on level 3. And then another command block will do the same thing, and another command block will do the same thing. And so all of the command blocks will be reading out of level 4 and writing to level 3, which means regardless of what order the command blocks run in, which we don't have much control over because I'm just placing them into the world. And they're going to run in whatever order I'm placing them in the world, and so I don't have much control over the scheduling. I'm not going into details there, but the point is the order that the command blocks run within each tick doesn't matter, because all of them are reading from level 4 and writing to level 3. And so they're not going to step on each other's data, basically. And so in that iteration, that's what's going to happen. And then in the other iteration, basically what we're going to do is just the opposite. We're going to read from level 3 and we're going to write to level 4. And so during that iteration, once again, everyone's going to be reading from the same data and everybody's going to be writing to different data, and they won't step on each other's computations. And that's how we manage to do things, just having the command blocks run all during a tick. Doesn't matter what order they are, and they're not going to step on each other's data. So in any case, check1 body is one portion that runs in one tick, and check1 part 2 is the other portion that's going to run in the other tick. So next, let's look at the check1 body function, and it's about as simple as you could imagine, and this is kind of the core of the life algorithm right here. First off, I'm going to call a function called countNeighbors that we'll take a look at in a moment, but it is just going to populate the variable n in the scoreboard with the number of neighbors who are nearby, some number between 0 and 8. Number of live neighbors. And then it is going to clone from level 4 down to level 3. And basically what that says is I'm going to take whatever my current value of whether I'm alive or not, if I'm a black wool or a white wool, and I am going to write that into the cell for the next tick as kind of like the default value. And so basically we're starting out with the default value that says, if I was alive, I'm going to continue to be alive, and if I was dead, I'm going to continue to be dead. And then we're going to make some changes to that based on certain neighbor values. The next line, execute at s, score n equals 1, detect wool 15, set block wool 0, basically translates into if there was wool 15, which is black wool, so if I was alive, and score n equals 1 means n has a maximum value of 1, which means I had 0 or 1 neighbors. That means this cell is supposed to die of loneliness. And so we set block at level 3 into the double buffer that we're writing, set it to wool 0, set it to white wool instead. So basically, that is the case of a cell dying of loneliness. And the next line is a case of the cell dying of overcrowding. Once again, it tests for a live block. It's detecting wool 15. It's checking if the neighbor score is at least 4 or greater, a minimum score of 4. And if so, it's going to die of overcrowding. And we note that it has died by writing white wool, which is wool 0, which is at the end of the command. And finally, the last line is for cells being born. So if I detect wool 0 in the middle of the command, you will see if I was a white cell, if I was currently not alive, but I had exactly 3 neighbors at the beginning of the command, score n min equals 3 and score n equals 3, then I'm going to set block on level 3 in the double buffer where we're writing. I'm going to set it to wool 15. I'm going to set it to black. And those are the only possible changes. We start out by assuming we're in the same state, and then if we were alive but we died of loneliness, we change it to wool 0. If we were alive but we died of overcrowding, we change it to wool 0. And if we were not alive but we had exactly 3 neighbors, we change it to wool 15 and we change it to black. And that is the core of the life algorithm right there. And that function that we just looked at called a function called countNeighbors, and countNeighbors is as dirt simple as you might imagine it to be, which is basically we start with n equals 0, and then we look at x negative 1, z negative 1, and x negative 1, z0, and x negative 1, z1, and basically look at all 8 neighbors that surround a particular square, and for each one that has a live block, each one that has a wool 15, we add 1 to the neighbor count. That's all there is. So we just looked at the first half of the loop, the one thing that runs on one tick. We need to take a look yet at what runs on the other tick, since we have 2 different processes. They're running on alternating ticks. And so the first process that we just took a look at basically computes exactly what the screen is going to look like in the next tick and writes it to level y equals 3. Now, the other alternating process, what it needs to do is it needs to do the double buffering. It needs to take what was written at level 3 and clone it up to level 4 so that we can actually see it. And it needs to compute where we are going to need to do processing in the future, where we need to leave command blocks. Because once again, anytime there is new life in the world, such as when I use the bat egg, we go and we put command blocks under it so that I can actually do processing to detect if anything needs to happen there. And similarly, if we have just written some new life blocks into the double buffer at level 3, we need to detect those and write new command blocks down there as well. So the next function we're going to take a look at is called check1 part 2, which is not a very good name, but basically it is the process that runs on the alternating tick. And it does what I said. The first line clones from level 3 up to level 4. It basically takes whatever we computed in the previous tick and now actually moves it up to the screen so that we will be able to see it. Then it is going to detect from level 3, from the buffer, wool15, a live cell, and if it does, it's going to fill a 3x3 area below it with the command blocks that call check1, which once again is the only thing that a command block will ever do. It's going to call check1. And so it's basically doing the exact same thing that happens when I place down a bat egg. Anytime there is a new live cell in the system, we are going to put some command blocks below it so that we schedule that we have to go and do some processing over in this region of the whole infinite plane. We only want to do processing where there's actually live blocks and there could be something happening in the life simulation. And so we put some blocks there. Next, looking at the code again, it calls a function called Conway has buffer neighbor. And basically what that is going to do is figure out where we can get rid of command blocks. And so if I'm looking out in Minecraft again, over here I have these 3 lonely cells that have a bunch of command blocks beneath them. And you will notice if I run the simulation for a moment, all of those guys die. And if I go back down here, all the command blocks that were below them have disappeared. And that's very important. We need to get rid of command blocks that we're no longer using. Otherwise, as life was simulating, we'd just be filling the entire world with command blocks. And even if those command blocks, all had white wool above them, they'd still have to do all of this processing, and they would lag out the game more and more and more as there were more and more command blocks in the world. And so we need to get rid of command blocks where they are no longer needed. And the place where they are no longer needed, I should have done this to start. And so if I have something like this square right here in the middle is white, and all of its neighbors are white, which means there is no possibility that I will ever be changing this square in the next step of the simulation, because it's white and all of its neighbors are white. There is no life nearby. It's impossible in the next tick for this thing to come to life. And so that is the condition. Basically, when you are dead and all of your neighbors are dead, that is the condition that you know that you no longer need to do processing in this particular cell. And so I might even be able to, if I can switch back and forth in my inventory fast enough. I haven't thought about what the rest of the simulation is going to do here, but if I do this, I had ended up erasing all the rest. Yeah, but basically you would have seen in the very first step of the simulation, the center cell would have disappeared because it would have immediately noticed that all of its neighbors were white, and so it would have erased itself from existence. And unfortunately, this thing runs very fast, and so it ran 2 or 3 steps of the simulation, and the rest of the life ended up annihilating itself for other reasons. So now that we've said all that, let's go back and take a look at the code in check1 part 2. So the first line, again, was just cloning things from level 3 to level 4. We've computed everything that goes in the next frame to put on the screen, and so we're putting it on the screen. Then we said if there is new life, we need to put command blocks so that we can make sure that we are processing that new life. Then we called this function has buffer neighbor, and basically that is something that is going to detect basically if there's a 3x3 area right above us that is all white. Basically everything has died in this area. And if it was true that everything has died in this area, then the neighbor score will be 0. We'll take a look at has buffer neighbor in just a moment. And so if the neighbor score was 0, we're going to set block 1 at level 1 to air, and level 1 is where the command blocks are. So that is the code that deletes command blocks when they are no longer needed because there's no longer life at this location or anywhere nearby. And so let's go ahead and move on to hasBufferNeighbor now. Here's the code for hasBufferNeighbor. It looks a whole lot like the code for countNeighbors. There's just a couple of notable differences. One is it's doing the detecting at layer 3 rather than layer 4, because this is running on the alternate tick. We are reading from the buffer on layer 3 rather than reading from the world on layer 4. And another difference is it's checking all 9 positions, not just the 8 neighbors, but also the cell itself, because we're looking for a whole 3x3 area that is completely white. And finally, just for efficiency, some of the executes are guarded with score n equals 0, because once we find at least one neighbor, we can stop executing this. All we care about is, are there 0 or are there more than 0? And so once it becomes more than 0, we can stop kind of doing more processing. And at this point, we've seen all the code. Once again, I'll just kind of summarize the 7 functions. Initializes scoreboard objectives and summons the armor stand. Life is the main function, which doesn't do a whole lot other than kind of making sure that the running variable and the alternating between a equals 0 and a equals 1 runs, as well as giving me the opportunity to use things like the bat eggs to set up some initial squares and the skeleton eggs to go ahead and erase some of those squares. And then there is check1, which is the main kind of life function, which computes the next life value based on kind of the life algorithm. It uses countNeighbors as a helper in order to figure out how many neighbors a particular cell has. And then there is check1body, which does the double buffering portion, which basically does the work of copying the wool from the buffer back up to the visible screen, as well as scheduling the work for the next iteration. When it sees black cells coming up, it adds new command blocks into the world, and when it sees 3x3 areas of white cells, it deletes the command blocks from the world so that we don't waste time computing where we don't need to compute anymore. And it uses hasBufferNeighbor as a helper inside that one. And check1 is the thing that calls both of those directly, and it teleports the armor stand to its location so that we actually have an entity that we can use for doing all the relative checks that we do. And that's all there is to it. And so that is the game of life in Minecraft. Stepping way back into kind of the big picture, what is interesting to me from a computational point of view of this system is just the observation that now that a single command block can call a function, that means that if you are at liberty of putting command blocks into the world, you can use that to schedule interesting computation in the future. And you can imagine using that in systems in survival kind of worlds as well. If you're doing stuff with terrain generation, you could, put some command blocks down at level 0 where things would normally be bedrock, and have a repeating command block there that is maybe turned off most of the time, but turns itself on if the system isn't lagged out, and maybe is keeping track of how many ticks this area of the terrain has been alive so that you know if it's new terrain or old terrain, and it's something that people might have already built structures in, or is something that is freshly new and a player has just seen it on the horizon for the first time. If you're trying to then, put in new structures, if you're doing something crazy with the terrain generator, just as a for example. And so the key observation is if you can put command blocks into the world, you can basically schedule interesting entire algorithms in the world that will happen at certain locations at certain periods in time. And so that's a new way to think about kind of how you structure computation overall inside of Minecraft. And that's what's interesting about this example, in my opinion. So I hope, as always, that you guys are having a great day. I hope you learned something from this example. I know some people will ask about a world download. I'm not giving one. We're in pre-5. The way that Mojang works, they're just going to break something tomorrow again. And for the next 4 years, I'm going to have people asking a question on this video saying, I downloaded the thing and it doesn't work right now. And I just don't want to deal with that. You've seen all the code. You can replicate it yourself. All you need is a super flat world that has wool at level 4 and air above that, and you're ready to go. So you can do it yourself. I hope, as always, you guys are having a great day. Bye. Bye bye.